see your tax returns.
I don't want to see my tax return. Okay. All right. Let's see if this works. It's on. And then... perfect. Okay. Thank you. Good morning, everyone. It's great to be here and see everyone for the summer school. I want to again reiterate my thanks to the organizers and everyone here at ESI for getting us all together. So as Mikhail said, it's the summer school. I want to start by encouraging, sort of echoing what Mikhail said, encouraging people to meet each other, not just the students at coffee breaks, but also if, as a student or a postdoc, you want to meet some of the senior researchers here. Please feel free to introduce yourself. There's plenty of time in between the talks to do so. So don't be shy. Another thing that I'll do is encourage. See, it's pretty daunting here. I have these slides, and I'm not even done making them. And I think it says 92, right? So anyway, I don't have to get through 140 of them today. But so I encourage, if you have questions, to stop and ask, or save them for coffee breaks if you like. Just so you know, the notes will be, or the slides will be posted somewhere online, so you don't have to feel like obligated to try to write down everything in real time. Please don't. Today I'll use the slides, and I might do it tomorrow too, or if I'm feeling particularly frisky, I'll use the chalkboard. We'll see how we're doing. Okay. So as the first lecture for the summer school, I feel like we should do some sort of background. Someone should present sort of the setting of the constraints and the setting of the Einstein equations. The stated prerequisites for the school were, some Riemannian geometry and some relativity. So that's what I kind of assume. If you're an expert, you should already know this. You do. If you're a novice, it might go a little fast, but hopefully you'll appreciate some of the connections, whether you're coming from physics and looking at some of the math involved, or you're coming from mathematics and don't know the physics of Einstein's equations. Maybe you catch something interesting. So all right. So the overview of my sort of 4 talks. So first, I want to sort of introduce and motivate the Einstein constraint equations, and sort of tell you where they sit in the context of general relativity. In particular, so one thing I thought about doing is just writing them up and saying where they come from, and then just starting to solve them. But I think it's instructive to explore the role of the constraints in the initial value problem for Einstein's equations. And so hopefully at the end of the hour, we'll have sort of seen a connection between the constraint equations, whose analysis and geometry we'll be exploring this whole week, the connection between those equations and the initial value problem for Einstein's equations. So all of that is sort of the background, and then I want to introduce and explore some approaches for solving the Einstein constraint equations. In particular, we'll look at the conformal method as well as some non-conformal techniques to do gluing constructions of solutions of the Einstein constraint equations. Okay, so again, part 1, which we'll start with momentarily, is we'll look at where do the Einstein equations come from an Einstein-Hilbert action. And then once we have the Einstein equation down, we'll derive the constraint equations, and then put the constraint equations in the initial value problem. So after we've done the background, then we want to talk about constructing solutions of the constraints. And the first method we'll look at is using what's called the conformal method, or conformal techniques, to solve Einstein constraint equations. If you know some PDE, the constraint equations are elliptic, and so as opposed to the space-time Einstein equation, which is essentially hyperbolic, so they have sort of different characters to them. But one thing we'll do is discuss the basic framework of the classical conformal method of Licknerowitz, Choquet-Bruhat, York, describe the CMC case in some detail, and then start doing gluing constructions. And the first one we'll do is using conformal deformations. After we've done that, in the last 3.5 minutes of the fourth lecture, we'll do all of this. No, hopefully not. So after we've used the conformal method, I'll discuss what goals might be to use. So what kind of problems you want to solve, what kind of data you want to construct that might lead you to try to use non-conformal techniques. And we'll look at deformation of scalar curvature. We'll focus on the scalar curvature. If there's time at the end, I'll look at the full constraints operator, but talk about sort of localized deformations of scalar curvature and how you can use those deformations to do localized gluing constructions for initial data. And such kind of constructions, sort of throw this out there at the beginning, might be if you have a number of isolated gravitational systems you're studying and you want to try to put them together into one system, sort of connect them together into one solution to the constraint equations, the initial value conditions, and then evolve the system from there. Then that's asking for a gluing construction. So maybe taking these solutions and putting them together. Now the constraints, as we'll see momentarily, are just like Einstein's equations. They're nonlinear. So there's not just a simple superposition principle that you can use, and that makes it difficult and that makes it interesting. As time permits, we'll look at the full constraints operator in the context of the gluing problems and the Hamiltonian formulation of the Einstein equation. But we'll see where we are in a couple days. All right, so the title of this slide is Obligatory Curvature Convention slide. Someone had to do it, so since I'm the first lecturer, I'll put this up here and quickly turn the page. But just, so everyone uses the curvature is this tensor or it's negative. And then once you get to the second line for index conventions, all hell breaks loose. And we have a mad scrum. But anyway, here's a standard kind of index convention for the curvature tensor. It's a 1-3 tensor. At least things start to settle down once we start taking this big tensor and tracing it. So an important curvature is the Ricci curvature, which is a trace of the full curvature tensor. And that leaves you with a symmetric bilinear form, the Ricci curvature, and that plays an important role. So it's a partial trace of the curvature tensor, and then you'll see this a lot in the constraint equations. We'll be studying the role of the scalar curvature operator this week, and that's the trace of the Ricci. So it's the sort of the full trace of the curvature tensor. So in the slides, if you see a comma anywhere, it's a partial derivative, but a semicolon denotes a covariant derivative. Okay, so for example, if you have the metric, it has 0 covariant derivative. All right, so that's just some notation. All right. Okay, so here we go. So what is the vacuum Einstein equation? Well, it's Ricci of the metric is 0. Okay. If you have a Lorentzian metric, G bar, then this is a sort of a nonlinear second order PDE system for the metric. And where does that equation come from? So you could, I don't have time to do this, to sort of try to go through historically how this equation was derived in terms of Einstein's development. Instead, I'll focus on the geometric analysis kind of point of view. Is bless you, this is the Euler-Lagrange equation for this action. So you take the metric and you look at the scalar curvature of the metric, and then you integrate over the manifold. Now, if the scalar curvature is not in L1, then the variation still makes sense, as I'll make clear on the next slide. But so you look at this action, it gives you sort of a functional in the space of metrics, and then we're going to look for ones that are stationary for that action. So we want to basically vary the metric. So we want to take the metric g bar and vary it in the direction of h, and then look at the first variation of that functional. Okay. To do that, you need to differentiate the scalar curvature and the volume form. Okay, both of which are standard calculations. So again, you've either done these before or you haven't, and again, you don't have to jot them all down right now. If you haven't done them, they're important calculations to do. In particular, I'll point out the linearization of the scalar curvature operator written here will play an important role in the analysis for a number of the talks. And so it says that this L operator on the first derivative of the metric, or sort of the first variation of the metric, is Laplacian on the trace of the tensor. Remember, the metric is a symmetric, non-degenerate tensor. So H bar is a symmetric 0-2 tensor. So you take the Laplacian of the trace, you take double the divergence, and then you dot the H bar with the Ricci. And that's the variation of the scalar curvature, and that operator and its adjoint will play an important role. The volume element involves a square root of a determinant, absolute value, and you have to do a standard calculation to vary that volume element, and you end up with a simple inner product between the variation and the metric. So it's just a trace. Okay. So if you haven't derived the Einstein equation, we're almost there. Imagine taking this action and taking a derivative and use the product rule. There's going to be two terms. One's going to come from the scalar curvature. One's going to come from varying the volume form. And we're going to take H to be this variation, let's say, to be compactly supported away from the boundary. And if you do that, then when you integrate by parts, when you use Stokes' theorem, these two terms, the Laplace term and the double divergence term, integrate to 0. So that all you have left in your variation is a Ricci term and a trace term. Okay? So, here we are. So the first variation of the action involves the Ricci term and the trace term. Okay? And if you organize it this way, this tensor here, the Ricci tensor coming from the variation of the scalar curvature, and the 1/2 scalar curvature times the metric term coming from the variation of the volume form, this combination of those tensors is the Einstein tensor. Okay. And so the Euler-Lagrange equation for the Einstein-Hilbert action is that the Einstein tensor vanishes. All right. The Einstein tensor is divergence-free in any case, in general, and the Einstein equation is that it vanishes. And if your dimension of your space-time or your manifold is at least 3, then by taking a trace of this equation, g equals 0, you get that the scalar curvature of g bar is also 0, which gives us our Einstein equation, Ricci g bar is 0. Okay. Now, Einstein metrics are metrics more generally for which the Ricci curvature is a constant multiple of the metric. And in terms of physics, this lambda would be, say, a constant, cosmological constant, let's say, and you could modify the Einstein-Hilbert action by taking the scalar curvature of the space-time and subtracting off twice lambda, putting that into your Lagrangian. And if you go through the same calculation, then the Euler-Lagrange equation for this thing is the Einstein equation, Ricci equals lambda g. Questions? So take a quick sort of side detour. Variational problems involving the total scalar curvature are very important, not just in relativity, but in Riemannian geometry more generally. And I'll just mention sort of two other ones. So first of all, let me say that if I have a closed Riemannian manifold, so closed means compact and no boundary, and dimension at least 3, let's say. M1 will be the set of metrics of unit volume. So the total volume is 1. You can always rescale to have the metric to have total volume 1. And so when we have bars, sort of these brackets around G, that'll be the conformal class of G. So all metrics that are conformal to G. So conformal means take the metric G and at every point multiply by a scalar f depending on the point. That gives you a metric conformal to G. Okay, so we can look at the Einstein-Hilbert action, the total scalar curvature. We can look at R bar, which is the total scalar curvature sort of normalized to metrics of unit volume. Okay. And so you can look at sort of these constrained optimization problems. Critical points for the total scalar curvature are Ricci 0. Critical points for the normalized curvature, okay, are Einstein metrics. So critical points amongst unit volume metrics. And then if you look at the unit volume metrics in a conformal class, so only restrict to metrics which are in a conformal class, then a critical metric is CSC, constant scalar curvature. Question?
If you talk about unit volume metrics, you need a background metric where you have to fix a volume, otherwise it's coordinate dependent.
You use the volume measure coming from the metric?
Yeah,
right.
It's a measure. So what's unit then? You need something to measure against. You must fix either a volume or a background Riemannian metric.
Okay, yeah, sure. Okay. I mean, right. Or you could just look at this action here on the space.
Yeah.
Yeah.
I mean, vol G is not a function. It's a density.
It's a number. Yeah. No. The volume is just you integrate the measure. So I'm not looking at the volume measure, it's the total volume. Yeah, the total volume is 1. Yeah. Okay. All right, so thus far we've basically been looking at sort of vacuum Einstein equation, which is oftentimes geometers look at the vacuum equation. I'm not going to spend much time on, or really any time on matter models, but if you have a matter model, you would sort of change your action and put in the Lagrangian modeling the matter, whether it's Einstein-Maxwell fields, scalar fields, Klein-Gordon field, whatever field you have, whatever matter, would get encoded by this Lagrangian. Then you take your previous action that we used, and then we normalize by a constant 1 over 2 kappa, where kappa in 4 space-time dimensions would be 8 pi g over c to the 4th. So what you'll see in most of the lectures, so that Newton's constant and the speed of light would be normalized to 1. So you'll see kappa being 8 pi, so 16 pi. So when you see factors of 16 pi running around in some of the energy expressions, you might trace them back to here. In any case, if you then compute the variation of this functional in the metric g bar, what you get is, of course, in the first part, you get the Einstein tensor from before with the lambda, and then the variation of the Lagrangian for the matter gives you, by definition, what's called the stress energy tensor. It's automatically divergence free. Okay. If you look at the variation and you ask it to be stationary for varying the fields, then you get like the equations of motion for the matter fields. Okay? But if you just vary the metric, then the first variation is written this way, and then Einstein equation becomes the Einstein tensor with the lambda equals a constant times the stress energy tensor. Okay? So that's right. So there's the Einstein equation with the cosmological constant. As it's written, without a specific matter model in mind, it's sort of, anything satisfies an equation of that form just by defining T to be the left-hand side of the equation, and it satisfies it. So that's not maybe not so interesting on its own. Usually, you either have a matter model in mind, for example, T is 0 is vacuum, or, and you'll see this come up in some of the other lectures, especially, you put at least some energy condition on T. So you make it be reasonable from a matter model point of view. And then it's actually then interesting that that has sort of geometric consequences for the constraints. So one energy condition would be called the dominant energy condition, which plays a role in the positive mass theorem. One way to say it, and we'll write it in terms of initial data shortly, one way to say it is, if you have your space-time, and when you have a space-time metric, the tangent vectors to the metric, as you know, so there's a light cone. Certain vectors are space-like, certain vectors are null, and certain vectors are time-like. So for future-directed, if you have at least locally a direction, that's the future. For future-directed time-like vectors, this vector, so put the vector xi into the stress tensor. Minus signs are all over the place. You have to be careful. But this vector is future-directed causal. Another way to say it is for time-like or causal vectors in the same time cone, sort of in the same time direction, you have a non-negative value of the stress tensor on those vectors. So it's giving you some sort of non-negative energy density as observed, moving in some direction. And so that kind of energy condition gives some interesting geometric consequences and is satisfied for the classical models that are used in physics.
Sorry, what is the signature of your metric?
So space-time, I should have said. That should have been on my obligatory slide. So, right. So it's so for a Lorentzian metric, it'd be 1 minus and then pluses. So so the time direction is the minus and the rest are plus. Sometimes it's the reverse. Okay, so that's the Einstein equation. We want to work toward the Einstein constraint equations, and so I have to introduce a little bit about the geometry of submanifolds. So if the board is the space-time S, then the Einstein constraint equations are going to live on a hypersurface, M or sigma, depending on your notation, sitting inside the space-time. This hypersurface will be taken to be space-like, which means the induced metric on the surface will be positive definite, and we'll have a local time-like unit vector, normal vector n. So in the metric, the dot product of n with itself is -1. So that's the sort of situation. The constraint equations are going to live on a space-like hypersurface inside a space-time. So we want to sort of understand the geometry of the hypersurfaces in a Riemannian, or for spacetimes, Lorentzian manifold. Okay? And so essentially, if we start with a metric g bar on the space-time, that induces a metric g called the first fundamental form on the submanifold M. Okay? And we also get a second fundamental form as follows. So as you know, for any metric, you have a connection associated to the metric. And so if you're in the space-time, you have the metric, the connection del bar. Okay? Now, if you take that connection and you act on it on directions tangent to a submanifold or hypersurface, you get a vector that you can decompose into tangential and normal components. Okay? So, great. So what you get is the first piece, the tangential piece, is exactly the Levi-Civita connection on the induced metric. So it's the covariant derivative on the hypersurface, submanifold. And the normal piece is called the second fundamental form. Okay? So, as written here, this second fundamental form is vector valued. It is just the normal component of a vector. All right? And although derivatives themselves aren't tensorial, differences are. So the second fundamental form is tensorial, and actually it's symmetric. Okay? It's actually symmetric. So at this point, there's no disagreement on what the second fundamental form is, the vector valued second fundamental form. On the next slide, all hell breaks loose again. So, so again, the second fundamental form, we're going to turn it into a bilinear, symmetric bilinear form, scalar valued, and there's a couple of ways to do this, and they differ by a sign, possibly. And when you're reading the literature, you have to always ask, what's the sign if you care about those things. So, and sometimes it matters. So, given the vector valued second fundamental form, all right, so we have a hypersurface. The second fundamental form is a normal vector. So in a hypersurface case, the second fundamental form is a multiple of the normal vector. All right, so one natural thing you might do then is take that normal vector and then peel off the scalar and call that your scalar valued second fundamental form. So that's quite natural to do that. I put a k hat over it because another way you might do it, maybe like if you're coming from a Riemannian geometry class, is to define the second fundamental form using what's called the shape operator, and that's usually defined this way. You take your covariant derivative and look at the normal component by dotting with the unit normal vector. And of course, that'll give you the same answer in the Riemannian case, where the whole metric G bar is Riemannian. But in the Lorentzian setting, n dot n is -1. So k and k hat will differ by a sign. Okay? So you have two of these running around, and depending on where you're reading, it could be either one. So folks who are, equations like this one are very important. We use the product rule on covariant derivatives and the metric to move this covariant derivative onto the y and change the sign. So that's just the product rule. Make sure you understand that. All right. So the Einstein constraint equations come from looking at the fundamental equations for submanifolds that relate the metric to the geometry on M. So we have the first fundamental form will be G, and we have the second fundamental form in one of its guises on this metric. And we have the extrinsic metric. And we want to relate, so the fundamental equations relate G and K and the ambient metric and the curvatures of those things. Okay? And once we understand those equations, we can get the Einstein constraints. All right? So the Gauss equation involves looking at the curvatures purely tangential to the slice. So we're going to look at the curvatures of the submanifold and then the curvature tensor of the ambient manifold along directions tangent to M. Okay? And look at their difference. And classical equations say the difference comes out by this kind of determinant of components of the second fundamental form. In the hypersurface case, you can replace these second fundamental forms by the scalar valued second fundamental form, and this might look a little more familiar. Again, in the Riemannian setting, n dot n is 1, and you just have the classical Gauss equation. All right, so let's prove something, hand wavy. Let's prove the Gauss equation. Okay, indicate the level of difficulty if you haven't seen this. So I don't know, again, people's backgrounds, so if you've seen this 10 times, I still want to apologize. But certain places sort of write up the proofs of something, the derivations. Not that you're jotting it down or whatever, but just to sort of connect to say, what is the level of difficulty that you have in doing a proof of something? Later on, there'll be PDE proofs, and the level will be, a different level altogether. The Gauss equation is quite important. The proof proceeds by just decomposing all the terms. So let me go back a second. So the Gauss equation has the curvature tensors of the extrinsic and the submanifold. So we just write down the definition of curvature and expand. So here's the curvature tensor, and then like these terms, the covariant derivative terms, can be decomposed into tangential and normal. So for example, this first term, there's a del x on the outside, and del yz can be decomposed into tangent and normal. And same for the second term. In the third term, I already took away the normal component of del bar because w is tangential. So when you dot product, the normal component, that doesn't matter. So once you do that, you then do it again. If you compute del x on this vector, right? So if you break it apart, the derivative of the second fundamental form term is here. And then you have a derivative on del yz. And that can be written out into tangential and normal components. Okay? You do that for this term as well. And then you dot it all with w, which is tangential. And when you dot it with a tangent vector, the normal component disappears. So all you have left is this term, the del y del x term, which gives you the curvature tensor of the submanifold. And then you end up with the derivative of the second fundamental form term dotted with w. Okay? And use the product rule again to turn this into a quadratic term in the second fundamental form. Okay, so it's a simple sort of derivation using the product rule and tangential and normal components. Okay? The Kodotsi equation involves looking at, instead of the tangential component of Rxyz, looking at the normal component. Okay? And that actually, the normal component, so just in the hypersurface case, the normal component of the ambient curvature tensor can be written in terms of the derivatives of the second fundamental form. Okay? I won't go through that proof, but it's a similar level of difficulty. Oftentimes you write these in index notation, and in particular, when I look at the Kodotsi equation written in index convention, it looks quite simple. You have this difference of the covariant derivatives of the second fundamental form, and all you've done is you've switched the I and j indices, and that gives rise to this normal component of the curvature. Okay, so you have the Gauss equation and the Kodotsi equation are fundamental equations on the submanifolds. For higher codimension, there's something called the Ricci equations, but we don't need those. Questions? And again, all this will be posted, so if you jotted something down and got the indices wrong, you can check it later. Okay, so the Einstein constraint equations, if you haven't seen them, so the Einstein constraint equations come from, so we now know in general when we have submanifold or hypersurface how the first and second fundamental form are related to the ambient curvature. We have those fundamental equations. If we then also say, you know what, the ambient curvature tensor satisfies an Einstein equation, we put those all together, that gives us the Einstein constraint equation. Okay? So in particular, let's think, for example, you want to study vacuum space-times, in which case you would know something about the ambient metric. Vacuum space-times, Ricci G bar is 0. So some equation on the ambient metric. You don't know the ambient metric. There are lots of, thankfully, we're modeling gravitation. There's lots of solutions of Einstein's equation. But maybe the ambient metric is vacuum, and you want to say, well, what does that imply for the geometry of the hypersurface? Is there any restrictions? Yes, it comes from the Gauss and Kodotsi equation. Okay? Okay, so before we write down the constraints, we're going to put the sort of, if there's a matter model, if there's a non-zero stress energy tensor, we want to sort of decompose it adapted to this hypersurface. So if you recall on an earlier slide in different notation, there was a condition called the dominant energy condition involving taking the stress tensor and putting in this time-like unit normal with the sign. And I'll call that vector J here. Okay. And that's a space-time vector. And I'll decompose it into the normal component, where the scalar normal component, the scalar is rho, and then a vector component tangent to the surface, which is J. Okay, so I'm taking this vector, which appeared in the dominant energy condition, and decomposing it into tangential and normal components. Okay. All right. So it's easy to see by putting in another n here and using the fact that n dot n is -1, that rho is TNN, that coefficient rho in this vector. And the dominant energy condition would say that rho is non-negative, as we had before. And that is, this quantity is the energy density of the fields so as measured by an observer with velocity c times n. So if you're an observer in the space-time and you're moving in this direction, then the energy density you measure is rho. And you say, well, that should be non-negative. Well, that's part of the dominant energy condition. But remember, the dominant energy condition said that this vector, when you contract t with a time-like vector, right, the vector you get should be future-pointing causal, the whole vector. And that means that the rho must be at least as big as the length of j, like the length of the vector j. You need that to be true. And that's the dominant energy condition written in terms of the hypersurface. Okay? The rest of this, it's just me being careful about minus signs. I don't really. Okay, so essentially, rho is like t in the n direction, and j is t evaluated in the 0, that's the n direction, and I, a spatial direction. So you're looking at certain components of the stress tensor. All right, so then here, finally, are the Einstein constraint equations. All right. The first one, as we'll see, comes from the Gauss equation, along with Einstein's equation, and the second one comes from the Cauchy equations, which makes sense. You can see in the second one, you're differentiating the second fundamental form. Okay? So these are equations, okay, written like, where's the space-time metric there? It's not there, right? I mean, so these are equations sort of written on the hypersurface. So these are these divergences, the derivatives there, the scalar curvature of G. Those are all quantities involving the induced geometry of the manifold M. Okay? And so the first equation has the scalar curvature of the hypersurface. You can have higher dimensional spacetimes. If you want to focus on a 4-dimensional spacetime, then the M is a 3-dimensional manifold. Okay, and so you have its scalar curvature, and then some quadratic terms in the second fundamental form. And on the right-hand side, you've got, if there's a cosmological constant, there it is, and then the energy density. Okay. The second equation then involves this sort of momentum density. The little kappa? Yeah, that was in, so that's, let's see, what did I say? In 3 dimensions, it's 8 pi g over c to the 4th or something. So think of it, it's like an 8 pi. It's in the Einstein equation. So yeah, you want to think of kappa in this case as 8 pi in 4 space-time dimensions. Yeah. So in the vacuum case, so the T is 0, rho and J are both 0, and you don't have to worry about it. But let's just look at a couple of simplifications just to point out things that you'll see more in the geometric discussion, for example, in the positive mass theorem coming up. So let's suppose that we're doing the pure Riemannian case. So say, for example, the time-symmetric case where k is 0. That's got a lot of interesting stuff in it, too, even if you just assumed, which is generally not the case, but you assume that k is 0, and all you have is the g. And let's even take lambda to be 0. Right? And what happens then? Then you get r of g equals 2 kappa rho. So what you see is, in the pure Riemannian case, it's called, so when k is 0, the scalar curvature of the 3-manifold is proportional to the energy density. Under the dominant energy condition, that's non-negative. Okay, so you'll see over and over again in different talks this week situations where you assume scalar curvature non-negative, and it comes from the dominant energy condition. And it implies things about the geometry of these hypersurfaces. Okay. Now, you might think it's kind of getting too boring if we make everything on the right-hand side vanish and k vanish and just get scalar curvature equals 0. But that's an interesting equation as well. All right. So the time-symmetric vacuum case, no cosmological constant, scalar curvature 0, still interesting. Okay. All right. All right, let's do a proof. Okay. This equation is so important, I guess we can prove it. Again, if you haven't done it, it's worth doing and sorting out the minus signs. Okay. So again, let's go back. So I want to prove this first equation. Okay, so you got scalar curvature of the 3-manifold of the submanifold. You got some quadratic terms in k. All right. Okay. So you start with an orthonormal frame on the submanifold. You're going to take traces for the scalar curvature, so it's convenient to use an orthonormal frame. Okay. So if we take the total sum, I call the dimension of the submanifold m, because I'm already using an n. But anyway, okay. So I take this complete trace of the extrinsic tensor along the hypersurface, and I use the Gauss equation to break that apart. The Gauss equation tells you you've got that the ambient curvature in tangent direction is related to the hypersurface curvature tensor with quadratic terms in k. Somewhere there's a minus sign in there that I slipped under the rug, but you can sort it out if you care. Okay, but that's basically, that's just the Gauss equation. Okay? And then if you sum it up, this term here gives you the norm of k, or this term here gives you minus the norm of k squared. You're summing up the matrix elements of k squared in an orthonormal frame. That's just the square norm. K, ej, summed over j is a trace. So we have two trace terms. That's trace squared. So already that's the term on the left-hand side of the Hamiltonian constraint. Okay, that's just the Gauss equation. Okay, so somehow we have to pull in the Einstein equation. So for that, we need to know the Ricci tensor. Okay, so if we take the Ricci tensor of the ambient metric along a tangent direction of the hypersurface, what is that? You have to trace the curvature tensor. You put ej in the middle, and you trace over all the other directions. So tangent directions, all the i's, and the normal direction. But n dot n is -1. So that's why there's this sign here. All right? So now I'll take this summation on this side. I'll sum over all j. I'll move this term over to this side of the equation. What do we get? Well, we have the sum of the Ricci terms, and then we trace over all the j terms. That's just the Ricci NN. Okay? So we've got the left-hand side of this equation is the sum of these Ricci terms. Okay, so, oops. All right, so we have that our our left-hand side of our constraint equation, the sum of Ricci terms. Now, again, because n dot n is minus 1, to get the scalar curvature of the ambient metric here, the Ricci term has to appear with a minus sign. So I'll put it here, and then I'll compensate for it here with a 2. Now, the Einstein tensor without the lambda is Ricci minus 1/2 r of g bar. So if I put n, I contract it on the normal direction, and times by 2, that's just what this is. Okay, because we have a n dotted with itself as a minus sign multiplied by 2 makes that a plus. Okay, so if you look at the Einstein equation, then what are we missing from the Einstein tensor? We're missing the lambda part and the stress tensor t. So if we equate them here, we end up with 2 lambda plus 2 kappa rho. Remember that Tnn is the energy density rho. Okay, so we use the Gauss equation up here, a little manipulation, and here we use the Einstein equation. So, for example, again, if this is vacuum, then, so as we'll see shortly, G and K are going to be thought of as initial data for the Einstein, for an Einstein metric, initial data, that you want to prescribe. And the point to this kind of equation, the point to this equation is you can't prescribe it arbitrarily. G and K have to relate to each other. For example, even if this term is 0, it means that this combination of metric and second fundamental form terms has to combine to give you 0, for example. Okay? Oops, sorry. So the second constraint is called the momentum constraint, and it's proved using the Kodazzi equation. It's pretty direct. So it's kind of down here. It involves the divergence of K and the derivative of the trace of K. Okay, so that involves derivatives of K. So as you've seen, I remind you, the Kodazzi equation involves normal components of the curvature tensor, so it's not surprising that that is what's at play here. Instead of like leading you through the one step of the proof, I want to point out, though, that the constraints, okay, as we saw on the previous slide, the constraint equations really tell you about the ambient geometry being related to certain components, GNN. That's the equation we just saw on the previous slide when we proved the Hamiltonian constraint. And for the momentum constraint, GIN. So the Einstein tensor contracted in one normal direction and one spatial direction. Those components of the Einstein tensor, which you think of as a space-time tensor, those components can be expressed in terms of the data G and K. So those components, you can evaluate from knowing this hypersurface, not from knowing what's off of it. Okay. All right. So we have a few minutes to finish up the first hour, and then I get to abuse your good natures for another hour after this. So, but we have a coffee break in between. So let's set up a little bit for the next hour. There are lots of solutions of the Einstein constraint equations. Okay? Turns out there are lots of solutions of the Einstein equations, and then if you take any hypersurface inside a solution of the Einstein equation, you get a solution of the constraint equations. Okay, so all right. That's cool. We kind of want to turn this around and say, all right, let's start from solutions of the constraints and see if we can build up a space-time from there. Yeah. All right. Also, I should point out, it's listed here, the last sort of comment here. The constraints form an underdetermined system. So let me go back. Don't get dizzy here. Okay. Here are the constraints. The first equation is a scalar equation. The second equation is a vector equation. J is a vector, or one form depending on how you look at it. So in 4 space-time dimensions, you have 4 equations. The unknowns are G and K. Those are symmetric 0-2 tensors. Think of them as symmetric matrices. So you have more unknowns than equations. So the constraint equations give you an underdetermined system. In certain PDE formulations, you can also see that it's an underdetermined elliptic system. Okay? Okay? So that's good. That means we expect to have lots of freedom in constructing solutions, which hopefully then lead to lots of interesting spacetimes. Okay? So I'll start with, or I'll end the hour with 2 examples of spacetime. One of which you may not think is that interesting. The other one is very interesting. But we'll end with these examples, and then we'll start the next hour talking about the initial value problem. So the space-time you learn about in special relativity is Minkowski space-time. So that's a constant curvature 0 with, if the speed of light is 1, let's say, here's your metric. So what are the, so again, any space-like hypersurface in Minkowski space-time satisfies the constraints. So 2 canonical ones are, if you just take Minkowski space and then take a plane, like take t equals 0 slice, that gives you a solution of the constraints. Maybe not so interesting if you think about it, but it's flat. It's just Euclidean space. More interesting might be if you look in Minkowski space-time and look at sort of a light cone and then take a sheet of a unit hyperboloid. So that's given by this equation here in Minkowski space-time. That hypersurface is space-like. If this is the origin, the position vector from the origin is the normal. Okay? And you can compute the second fundamental form, and you actually get that the second fundamental form is basically the metric. And you get a solution of the Einstein constraint equations, vacuum, but the second fundamental form doesn't vanish. And the induced geometry on this hyperbola actually is unit hyperbolic space. Okay? There are constant curvature examples for lambda positive and lambda negative, which with current sort of cosmological models then are important to understand, but we don't have time for the. Sort of end with a very important class of examples called the Schwarzschild spacetimes. So if you look at the Einstein equation, Ricci equals 0, and you impose an ansatz of rotational symmetry. Okay? So you ask for the metric to depend, sort of in terms of a single variable r, distance from an origin, and then it has rotational symmetry. Turns out you can solve those equations. They reduce the Einstein equations to ODEs. You can solve them. I'm not about to do that in front of you. But if you solve those equations, you end up with what's called the Schwarzschild solution. There's a parameter in the solution m. It's called the mass. There's reasons for that, and we'll see the mass come up in lectures. M is sort of a constant of integration in solving. Actually, second order equations, you have another constant of integration too that's been kind of normalized to be 1. So you get a family of solutions. R is basically, you can think of as distance, so or r tilde. If r tilde goes to infinity, then you get, in the limit, minus dt squared plus dr squared plus r squared times the metric on the sphere, which is just the polar coordinate, spherical coordinate way to write the flat metric. So as r tilde goes to infinity, the Schwarzschild metric asymptotes to Minkowski metric. So it's asymptotically flat or asymptotically Minkowskian. Okay. So it also, you notice, it doesn't depend on time. So it turns out it's a static metric. If I want to produce a solution of the constraint equations, then I can just take t equals 0. So take the time equals 0 slice inside Schwarzschild. And so if you do that and disregard the first piece, look at the spatial metric that you get. That's the Riemannian Schwarzschild metric. And I'll end with saying, so first of all, with a simple calculation, either just in components or if you're more geometrically minded, you can make an argument without really using components, that the induced second fundamental form on the time equals 0 slice is 0. So it's a time-symmetric slice of the, a time-symmetric solution of the constraints. Since the Schwarzschild metric is vacuum, that means the scalar curvature must be 0. So as I said earlier, that actually is an interesting equation, and the Schwarzschild metric is an interesting solution. And we'll pick up with that after the coffee break. Thank you.